Hi! In this video we will see how to generate the Gcode files to realize a double-sided circuit. We will use FlatCAM version 8.5 and we will take a look at the various steps and settings to generate a set of Gcode files useful to realize a double-sided circuit. All the settings and the type of files generated that you will see in this video are not something set in stone. It's just what we use to be able to align the second side using the camera of our little machine. We start from the generation of the Gcode file for the top layer, the top surface. First, we open the Gerber file of the top layer. Then we select the Gerber just opened and we set the isolation routing parameters. In this case, we will set a diameter of 0.2 mm. Also, if our bits nominally are 0.1 mm, they will mill with a slightly larger diameter. We will execute an isolation routing with 3 passes. And, very important, we will set the overlap of the isolation traces to 0.4, meaning that the traces will be overlapped of the 40%. Having an overlap so high helps, especially when you have new bits, because the 0.1 mm bit diameter will be quite less than 0.2 mm when the bit is new, and the isolation tracer will be less than 0.2 mm. If there wasn't this overlap, there would be some parts of copper not removed, some very thin parts that may create big problems, for example short circuits, and these should be removed by hand, and on large circuits this is quite annoying. Then select Combine Passes, that will create a unique job for all the passes, and as a consequence a unique Gcode file, instead of multiple Gcode files. After you set these 4 settings, you just need to press the Generate Geometry button. What the software creates, it's a sort of graphic description of the passes. Selecting the isolation geometry, we can generate a Gcode related to the top surface. We use a working depth of 6 or 7 hundredths of millimeter, depending on the type of machine you are using and the bits you are using. These values are working well for us. Set a CFTZ for the traveling motions. Usually we do not use more than 1 mm, so 0.7 mm is okay for us. The feed rate is quite an important parameter, and it is difficult to set with a perfect calculation, because it's true that there are some guidelines that tell us how to set the feed rate depending on the tool dimensions, the number of cutting edges and other parameters, but in reality it depends very much on the chuck rotation speed and above all on the rigidity of the machine. For now we usually set a feed rate of 90 mm per minute. You are absolutely free and encouraged to verify if 90 or a smaller number or a bigger number are better for your needs. We set again the same tool diameter. This is just needed by the software tool to generate some graphical traces that will appear on the screen, to give you an idea of how the path will be after the machining. The spindle speed in this kind of machining has always to be the maximum. Remember that the spindle speed is really important, since higher spindle rotation speed will result in traces more defined. Clearly, using the spindle that we suggest, the rotation speed will be around 5000 rpm, and using a 3 cutting edges bit, the effective rotation speed will be about 50,000 rpm, that is a good speed for this kind of machining. Press Generate to get the actual machining path, obtained with the parameters set until now. As you may see, in blue there are the effective machining traces, while in yellow there are the fast travels. The fast travels in this version of FlatCAM do not seem to be optimized at all, and we didn't find a simple way to optimize them, so we accept them as they are. This means that the working will be slower, especially if there are many traces and many pads, because the travel to move from a machining point to another is quite complicated and slower than what it could be. When we have the CNC job, we select it and, essentially, we use a couple of expedients to allow this job to work properly with our little machine. Also in this case, the tool diameter is just a parameter for the graphical representation, and it's not really useful for the Gcode generation. Instead, it is really important to insert these two Gcode commands into the header of the Gcode file that will be generated. In this way, when the rotation speed of the spindle will be set, the driver will receive the PWM signal, and it will be ready to activate the rotation of the spindle, and as a consequence of the chuck. So, this command sets a minimal speed, S10, 100th of the maximum rotation speed, and we insert a pause of 2 seconds so that the ESC driver gets out of its idle state and gets into a ready to rotate state. At this point, we just have to press Export Gcode. I always suggest to separate the Gerber files from the Gcode files, so you might create a separate folder, parallel to the one where you store the Gerbers, and save there your generated Gcode files. Well, the top surface Gcode file is now ready to use, so we take a look at the second generation process. I'd say that we can remove the elements that allowed us to generate the top surface Gcode. We execute now the generation of the bottom surface file, the one that will be used to machine the bottom side of the board. Let's open the bottom layer Gerber. And we also need the Gerber of the profile, and now we will see the reason of this. When you execute a double-sided machining, you have to take in account that, if the Gerber has not been mirrored, it is necessary to modify the orientation of the bottom side, mirroring it respect to the one generated from the CAM processor of the CAD, used to generate the corresponding Gerber. We strongly discourage you from mirroring the Gerber instead of mirroring the working geometry. To do the mirroring, FlatCAM has a tool called Double-Sided PCB tool that you have to activate from the menu. And then, from the corresponding tab, you will have this part of the interface that will allow us to mirror the bottom layer. We will mirror horizontally, respect to the y-axis, since it's more convenient when you work it with the machine to mirror on the y-axis. Afterwards, we select box. That is a way to indicate to the software a boundary box. That is a way to determine which is the x coordinate to use to mirror around the y-axis. We select the profile, so that we will use the profile that is the outline of the board to get a boundary box, and afterwards we press Mirror Object. As you can see, the bottom Gerber is now mirrored. At this point, we don't need the profile Gerber anymore, so we remove it. And then the process of generation is equal to the one used for the top surface. We set the diameter, the number of passes, the overlap. We suggest you not to go down to 40% threshold because you may have issues. Select combine passes and then press Generate Geometry. The geometries are generated as before. One important thing is to always take a look at this view, since it will show you if the tool diameter is small enough to pass in all the points of the traces. If this doesn't happen, you will not see traces passing in very narrow points in between two connection tracks. Of course, Since on our machine the pitch between traces is set to 0.2 mm, it is recommended to set the layout rules of your CAD, the DRC rules, in such a way that do not allow to generate a circuit with space between tracks or track and pad, and so on, less than 0.2 mm. In this way you will be sure that using a bit with the diameter 0.2 mm, you will always get a machining that will produce a working circuit board essentially without short circuit. Let's go on. Generate geometry. We select the geometry that has been generated. I set the cut depth, modify the feed rate and keep the same tool diameter. I set the spindle speed to the maximum and finally press the generate button. At this point, let's generate the Gcode in the same way, using the same prepended commands and saving in the Gcodes folder with the name bottom. We have got a new generated Gcode for the bottom, and we can remove the used files and get ready for the next phase. Let's start now with the first file that will help us a lot with the alignment of the second side. The main problem when you create a double-sided PCB with a machine like TheAnt is to align the Gcode with the holes or the vias of our board. The main concept is that, since there are no precise mechanical reference points, when you turn upside down the board to work on the bottom side, you will lose every reference to the top side Gcode, or, in other words, the alignment between the bottom side Gcode and the board. To obtain this alignment again, our machine uses the possibility to determine some specific holes made during the top surface machining. We can use the centers of the holes as markers or reference points, insert this information in BCNC thanks to the micro camera, and finally get the alignment of the Gcode of the machining of the bottom side to the machining of the top side previously processed. So, let's see how to create the reference holes that will be later used for the alignment. We open the file of the drill layers, that in this case is an excellon file generated from a CAD. And we select the minimum number of holes that allows us to align the two sides using BCNC. 3 holes should be enough, but to further reduce the alignment error, we usually select at least 4 drill holes. In this case it's quite simple to choose. There are 4 holes for mounting the board with the spacers. You can see them since they are a bit bigger than the other holes and are located at the 4 corners of the view. Sometimes there is the problem that these holes do not exist, or the number of vias is very low or so next to each other that it's difficult to get a set of holes that can be used for the alignment. As a consequence, during the design of the board, it is recommendable to include some alignment holes, also in the external part of the board. That is not an issue. The important thing is to have at least 4 of them, and they should be easy to locate. They should not really be next to each other, should be distributed on the working area surface as equally distanced as possible. We select the drill view, and then we will select only the larger drill holes. That is easy to do since FlatCAM groups the holes by diameter. We just select the row with the larger diameter. After this, we set the KZ, taking in account the thickness of the board, that usually is around 1.5 or 1.6 mm, but you may also measure it with a caliper. You also have to consider that the drilling bits have a tapered tip, so it's not enough to set just the cut depth equal to the thickness of the board, but you have to add some decimal. In this way, the bit will be able to drill all the way through the board, and it will avoid smearing the copper on the bottom side. That's why we usually set minus 1.9 mm, taking in account that the sacrificial bed is an MDF board that is quite soft, so drilling this material is not an issue. We set the 8 for the fast travel at 0.7 mm and 60 mm per minute for the feed rate. We choose to set the rotation speed of the drill a bit lower than the maximum, but that is really depending on the drilling bit you are using, and you will eventually find your preferred spindle speed for drilling with experience. We generate the drilling path, and as you can see, it has been generated just for the 4 drill holes that we selected. In the same way as before, we select the generated view, prepend the usual commands, and generate the Gcode that we will call top align drill to clearly define the working phase when this file should be used. At this point we need the mirrored version of this pattern that we will use to align the bottom layer of the board. So we just leave the drill excellon file, we load the profile gerber and we use it to mirror the drill layer. Select the drill, use the Y-axis to mirror, select the box option and the profile gerber, and then execute the mirroring of the object. We have now the mirrored drill object. We remove the profile since we don't need it anymore. We select the mirrored drill and use the same larger drill holes for the alignment. This file will not really be used for any machining, it will just be used to align all the Gcodes used on the bottom side, so we just set a minimal cutting depth. Then we leave the rest of the parameters untouched and generate the pattern. As you can see, the path generated by FlatCAM is quite messy also in this case. As done before, we select the path and generate the Gcode with the same prepended commands. Let's now generate the Gcode file that will be used to drill all the holes and vias in the board. We have to consider the holes diameter, and in this case we have mounting holes, holes that are on the pads of deep packages integrated circuits, and holes used as vias. As you can see, we have a bit of different diameters. For the sake of simplicity, we will use a unique bit diameter to drill all the holes, and probably the mounting holes will be drilled again by hand, or we will create a pattern during the profile machining to get larger holes. If you have smaller holes diameter respect to the true hole components diameters, we suggest you to generate more than one Gcode file for the drill, predicting a tool change for every different drill machining. In our case, since the diameters are quite similar, since the vias are quite big in this example, we may use a unique drill bit for every hole. In this case, we will choose a drill bit with 0.8 mm of diameter. I remind you that we mirrored the drill layer since we will execute the drill machining during the bottom side creation process. Let's select the file and then select all the diameters. We set the cut depth to minus 1.9 mm, the fast travel 8 to 0.7 mm, the feed rate to 60 mm per minute, and the spindle speed to 900. Then we generate the path and generate the bottom drill Gcode file. There is only one more file to generate, that is the profile cutting machining. Let's load the profile gerber. We need to mirror it, since also this machining will be executed on the bottom side. We select the gerber, set the diameter tool of 1.0 mm, keep a margin of 0.1 mm and set the gap size to 0.4 mm. What is the gap size? It's much more easy to answer this question looking at the generated geometry, so we generate it. As you may observe, the generated geometry has 4 parts interspersed with some gaps. Why are the gaps used? They are used to avoid the board to get separated and moving during the profile machining, since the board will be anchored to the wall board. Then we select the geometry object and we set the cut depth to -1.8 mm, since we are using flat tip bits, and we can set depth just a bit more than the thickness of the board. We set the travel height to 0.7 mm and we set a lower feed rate to cut. We set 60 mm per minute. Let's set the tool diameter to 1 mm, the spindle speed a bit lower than the maximum to 900, and we choose to use the multi-depth option. This means that the cut will be executed in more passes, with a depth interval given by the depth of each pass. We usually set 0.6 mm depth for every pass, so that the board is cut out in 3 passes. And also in this case we select the path and generate the Gcode that we will save as bottom profile. At this point we have all the Gcode files needed, and we can start using BCNC. We will see all the machining during the next video, and we will see how to align using BCNC. Thanks to all the people who are supporting and inspiring us. Please keep following us, there is more to come, and we hope you will enjoy it.